Okay, so 12.7 is called the unit cell and the structure of crystalline solids. And what we're going to do is look really close sort of at the geometry of this regularly repeating pattern in crystalline solids and see what we can determine about physical properties of the substance based on the geometry of their structure. So the structure is going to be composed of regularly repeating minimal units. If you think of the microscopic picture of a crystalline solid, if you were to sort of draw that by tiling the same small component over and over again, what is the minimum size, the simplest figure that you can draw that will be sort of repeated over and over to reproduce the entire structure? That is what we call a unit cell. So a unit cell is the simplest, smallest representation of a crystalline structure. And if that doesn't make a lot of sense, we'll see some very fine figures representing the unit cells of different crystalline structures. So for any unit cell, we are going to ultimately find four quantities. So the first is the number of atoms per cell. And then the second is the coordination number. And the coordination number is a fancy word for how many nearest neighbors are there for any given atom. How many neighbors is it making contact with on all sides and therefore forming a bond with? So that'll be the coordination number, and it's different for different unit cells, which may be a bit of a surprise. And then 3 is going to be the relation of unit cell edge length to the atomic radius. And that will make sense in a moment. The relation of the unit cell edge length to the atomic radius, and then sort of numbers 1 and 3 are going to combine to finally give us the density of the material. We'll find the density of the material based on these other components. So with that, let's take a look at what a unit cell actually looks like. Here you see, and by the way, we're dealing with metals, crystalline metals primarily in this section. So on the left you see this repeating lattice. There's a crystalline pattern, and highlighted in light blue over here is like a cube that you might think is the smallest unit that you could repeat over and over again to reproduce the entire structure. But in reality, if you're a little bit clever, you can make an even smaller, simpler repeating unit. This one right here that sort of cuts each of the atoms up into small pieces. So this little tiny cube right here, if I were to place another one up on top and then another one down below and on either side and in front and behind, and continue that, placing these little pieces like tiles on a bathroom floor, you would be able to reproduce this entire structure. So this is a unit cell. It is the simplest structure that we can repeat to reproduce the overall crystal. And there are 3 different cubic types of unit cells. So there's a simple cubic, which is kind of represented 2 different ways here. They're just stacked right on top of each other in a cube. The body-centered cubic is going to put an additional atom right in the center of the cube. And what that does is it kind of pushes these corner ones apart, so the corner ones aren't actually touching one another anymore. In fact, this figure doesn't really emphasize that very well, But if we looked at the points of contact between these spheres, those corner ones are not touching each other anymore. There is a gap, and they're actually touching corner to center to corner. And so that's a body-centered cubic, or abbreviated BCC. And then there's face-centered cubic, which will put one atom right in the middle of each of the 6 faces of the cube. Sorry, 8 faces of the cube. No, 6. I can count. Sorry, 6 faces of the cube. So this is called face-centered cubic, and again, that pushes those corners away. You can see the gap much more clearly in this figure. And so where are the atoms actually touching? This upper right corner is touching the middle, which is touching the lower left corner. And that's going to be important in a moment. So let's look at these a little bit closer, and these figures are a bit misleading because remember your unit cells are actually going to cut through the center of the atoms, center to center. And that means that when we look at the simple cubic unit cell, it really looks more like this one on the right. Now I'm going to try to use my, oh, hold on a sec. Okay, sorry, I just ran to go grab a graphics tablet. We got this for my daughter for her birthday, but I'm going to use it here. Okay, so let's count the number of atoms in our simple cubic unit cell. Here in this corner we have, oops, uh-oh. Okay, apparently I should have practiced a bit with this graphics tablet. Okay, here in this corner we have 1/8 of a total atom. That's just the little 1/8 corner of the atom. And over here we have 1/8, and over here we have 1/8, and over here we have 1/8. It keeps thinking I'm clicking. Okay, over here is 1/8, over here is 1/8. Stop that. Over here is 1/8, and over here is 1/8. Ooh, this might not work as well as I had thought. So what we have is 4 times 1/8. Oh, sorry, not 4. We have 8 corners. 1, 2, 3, 4 on the top, and 1, 2, 3, 4 on the bottom. So this is an 8 times 1/8. That equals 1 atom. Hey, isn't that neat? So that's the first thing we wanted to know. What is the number of atoms per cell? And the next thing we need to know is the coordination number. How many atoms are in contact with each other here? For this, maybe it's better to look at the kind of full crystal structure on the left. If I pick an atom right here, I see it's got a neighbor above and below, to the left and to the right. And then we'll have to think three-dimensionally here a little bit. There's one behind it, and there would be one in front as well. And so that's a total coordination number of 6. Coordination number of 6. And then the third thing we want to figure out here is what is the relation between the unit cell edge length and the atomic radius. So we'll come back over to this on the right and recognize it from this corner. Oh, shoot. I think I keep accidentally hitting the buttons on the pen. I apologize. So from this corner, oh my goodness, that's infuriating. Maybe I'll just use my mouse. All right, so from this corner to the middle, oh no, it's happening with the mouse too. What a mess. Okay, 4th time's the charm. Oh, this is infuriating. I just won't click. I'm so sorry. From this corner to the middle is 1 atomic radius, and from the middle to that other corner is another atomic radius. And so what we have is that the edge length L is equal to 2 times the atomic radius R. L equals 2R. Okay, so that is the simple cubic unit cell. Here we have a body-centered cubic unit cell. So let's count the number of atoms. We've got the 8 corners that each contain 1/8. And so that's 8 times 1/8. And then we also have the 1 in the center. And so that 1 in the center is worth this whole atom. So this is going to equal 2. There are a total of 2 atoms in a body-centered cubic unit cell. Now let's think about the coordination number. If we look at for the points of contact between nearest neighbors, here we can see there is actually a gap between those corner pieces. And so what we should really look at is this one in the center. How many neighbors is it in physical contact with? Well, each of the 8 corners is touching that center one, and so the coordination number is 8. If we were to look at one of the corner ones instead, well, if you look over here, they're actually all kind of the same. We can only see this corner touching one, but you know, up here there'd be another, and over here there'd be another, and in the end it would have 8 neighbors as well. Now, how do we figure out the relationship between the length of an edge and the radius of an atom? Well, this gets to be a little bit complicated. So if I'm going to draw a line that makes contact from the center of one atom to the center of another atom, I would have to draw it from this corner here. Oh my goodness, that's infuriating. To the far corner on the far side over there. And so what you would get is something like corner to corner through the center of the cube is equal to 4 times the radius. And there's one radius from the corner to touching the middle one, and then there's 2 radii from one end of the middle one to the other, and then finally there's one last radius to that opposite corner. And this is maybe a better place to draw what 2 corners I mean. Straight through the middle opposite corners. Okay, so that's a good starting point, but where do we go from there? Well, I can draw a triangle like that, where now the edge length is one of the sides, and diagonal across one of the faces is the other side, and then this 4r is the hypotenuse. So we'll call this, we'll use Pythagorean's theorem and say 4, oh my goodness, I'm going to lose my mind here. Okay, we'll say 4r is that hypotenuse. We'll square that, is equal to L squared plus the diagonal squared. And what's the diagonal? Well, the diagonal is just the hypotenuse of a triangle that is made on the face. So let's redraw that face. Here's a face. There's the diagonal D, and it's made a right triangle with 2 of the sides. So we know that D squared is equal to L squared plus L squared. And so what we really have here is 3 L squared. The 1 L squared here, and then L squared plus L squared from that diagonal. Anyway, all this ends up with 4R squared is equal to 3L squared. We'll say that L will square root both sides and divide the square root 3 over. So L is equal to 4 over the square root of 3 times R. Okay, you don't need to remember that derivation, and I don't want to dwell on it too much. It's just geometry, and we'll show you a table in just a moment that will summarize kind of all of this. But 2 atoms, coordination number of 8, and L is equal to 4 over root 3 times R. That is for the body-centered cubic. And now we have the face-centered cubic. And the face-centered cubic is a little bit easier than the body-centered cubic. We can see here that the... sorry, let's back up a bit. Let's count how many atoms are in this unit cell. So we'll start with 8 times 1/8 for the 4 corners, plus we've got these half of an atom in each face, and there are 6 faces to a cube, so we'll say 6 times 1/2. That's going to equal a total of 4 atoms. Ooh, this tablet is nice when it works. There are 4 atoms. And then let's think of the coordination number. And it's a little bit tough, but these face-centered cubic unit cells, how many neighbors is it touching? Well, it's touching 1, 2, 3, 4 on the corners. It's actually also touching these 1, 2, 3, 4 ones in the faces behind it, and it will be touching 4 more in the faces in front of it, although you can't see them. And so this has a total coordination number of 12. So face-centered cubic has the most neighbors. There are 12 nearest neighbors that it's in physical contact with. And then we'll come back here. The diagonal is equal to 1 radius, 2 radius, 3 radius, 4. So the diagonal is equal to 4r. And remember, diagonal squared is equal to, we'll redraw this. Here's our diagonal. And the 2 unit cell edge lengths. So we know that d squared is equal to L squared plus L squared. And so we can say that the diagonal squared is equal to 2 L squared. And the diagonal is equal to square root of 2 times, times L. So we'll plug that in over here. The square root of 2L is equal to 4R. And, this will all simplify. If I take L, it's going to equal 4 divided by the square root of 2 simplifies to be the square root of 8. 4 is the square root of 16, and we'll divide by the square root of 2, so 16 divided by 2 is 8. L equals the square root of 8 times R. Okay, so let's summarize all of that. Simple cubic has 1 atom per unit cell, body-centered cubic has 2, face-centered cubic has 4. The coordination number of simple cubic is 6, body-centered cubic is 8, and face-centered cubic is 12. And then the relation between their edge length and the radius, simple cubic L equals 2r, body-centered cubic L equals 4 over root 3 times r, and face-centered cubic L equals square root of 8r. And this is really all you need to know. Kind of the derivations and things, it would be fine for you to kind of forget about. So this table 12.7 really summarizes the most important things that you need to know to solve problems here. You'll notice there's also a packing efficiency number here. So how much volume is empty space? They have different packing efficiencies. And the simple cubic there is the least efficient. Body-centered cubic is a little bit more at 68%, and face-centered cubic is 74%. And it's now been proven mathematically that that is the highest efficiency that you can get for spherical objects packing in a three-dimensional space. And so the face-centered cubic compounds are as dense as they possibly can be. If we look here, face-centered cubic is called a close packing arrangement of atoms because of that high packing efficiency. But it actually is not the only way to pack things in a close packing efficiency. And this is a little bit hard to really understand unless you've got like some ping pong balls that you can play around with packing in real life or something. But here on the right, we have a different way to represent face-centered cubic, and it's called cubic close packing. And we've kind of twisted the face-centered cubic unit cell in a way that makes a little bit more sense to talk about the layers. Here on the bottom, we have 7 atoms arranged in sort of a hexagonal pattern. And if you were going to pack the next set of atoms on top of it, you kind of have a choice of where you're going to place the next set of atoms. Are they going to be here, here, and here? Or are they going to be here, here, and here? In other words, is that triangle going to be facing toward you or facing away from you? In cubic close packing, you would kind of face the triangle away from you, and then the next layer you would face toward you, and then finally on top you would recreate the hexagonal pattern on the bottom. So cubic close packing has a pattern of like A, B, C, A. Now in hexagonal close packing, what you do is face that first triangle toward you and then just repeat the bottom. It's just A, B, A. This would continue A, B, A, B, A, B, A. Cubic close packing would continue A, B, C, A, B, C, A, B, C. It's a pretty subtle difference, and I don't know that it's terribly important for you to sort of grasp the three-dimensional shape of all of this. But I want you to just know that there are 2 different schema for close packing. Hexagonal close packing does not actually translate simply into a cubic unit cell, but it actually has the exact same packing efficiency, and it's very, very similar to cubic close packing. All right. So why do we care about all of this? Give me a second here. We can now answer some very intriguing questions. So I'm actually going to need the whole board for these problems. So we're going to answer 2 questions. How can we take a measured density and find the atomic radius, and how can we take an atomic radius and predict the density? And so polonium has a density equal to 9.196 grams per cubic centimeter. And it has a simple cubic structure. Based on this, can we find the atomic radius of polonium? And I think that's a pretty interesting prospect, to just measure the density and know its structure. Can we find out the atomic radius, which is a quantity so teeny tiny we could never measure it with a ruler. The finest digital calipers aren't going to go down to the size of a single atom. And so it's a pretty cool idea that we can, a very straightforward and rough measurement like the density can lead to very fine measurement like the atomic radius. Well, how do we do that? We need to recognize that the density is equal to the mass divided by the volume. Okay, now what is the density here is 9.196 grams over 1 cubic centimeter. But let's take that and sort of apply it on a teeny tiny scale. The density is going to equal, let's consider the density of a single unit cell. The density of the unit cell should be the same as the density of the whole material. It's just a very small sample of the whole material. So what is the mass of a single unit cell? Well, this would be the number of atoms, which is one atom in a simple cubic unit cell, times the atomic weight of a polonium atom. Because there is one polonium atom within a simple cubic unit cell, and so the mass is going to be just one one polonium atom's mass. And what's the volume of a unit cell? Well, that's just the length cubed. It's going to be length times width times height. The unit cell is a cube, and so it's L cubed. And now hopefully you can see where we're going with that relationship between L and R. So let's kind of change this. So we'll have the atomic weight of polonium divided by 2R cubed. And so the atomic radius is related to L for a simple cubic as L equals 2R. If we have L cubed, then we have 2R cubed, which is going to be the mass of a polonium atom divided by 8R cubed. Okay, so now we've kind of simplified it as far as we can, and we need to put in some real numbers. So give me a sec to look up the atomic weight of polonium. There it is. Okay, so we go to polonium and its atomic properties, and the atomic mass is 209 grams per mole. So we have 209 grams per mole. And by the way, we can see our answer. It says the atomic radius is 190 picometers. Well, that's not the answer that I have. Interesting. We'll see how that works out. Does it give a density? 9.196 grams per cubic centimeter. And, oh, it's body-centered cubic. Shoot. Polonium does have different states and phases, and I think I used the simple cubic example, so we'll ignore that atomic radius. Okay, it's not actually going to be 190. And it is not body-centered cubic for this problem. We're looking at a different phase of polonium that is simple cubic. But anyway, we found its mass. That is what matters. Make the periodic table go away. Now this is the mass for a mole of polonium atoms. And we know that 1 mole is 6.022 times 10 to the 23rd individual polonium atoms. Because remember, we're looking at a single unit cell, or in other words, a single polonium atom, not a mole of atoms. So that is the mass. We'll divide it by 8r cubed and set that equal to our density of 9.196 grams per centimeter cubed. So we can sort of bring the r cubed over to this side, and we'll bring the 9.196 grams per centimeter cubed to that side, and we can solve r cubed. What does r cubed equal? It's going to be 209 divided by 6.022 E23 divided by 8 divided by 9.196. Okay, and so you can see that's 4.72 times 10 to the negative 24th centimeters cubed. And that's going to be important. The centimeters cubed comes from our density, which is given in units of centimeters cubed. So now we're going to take 4.71755 e negative 24, and we're going to raise it to the power of 1/3. In other words, we'll cube root it, and I'm going to get r is equal to 1.677 times 10 to the negative 8th. Now that's centimeters. And if we wanted to convert from centimeters to meters, then we would say 100 centimeters is 1 meter. So we'll just divide that number by 100. And so we end up with r equal to 1.68 times 10 to the negative 10th meters, or in other words, 168 picometers. 10 to the negative 9th is a nanometer. 10 to the negative 10th is hundreds of picometers. So, and that matches the true value, at least when you consider the simple cubic example. So I think this is really cool that you're able to take such a sort of crude measurement as the density of polonium. You can measure that easily. I could ask you to measure the density of a sample of polonium, and you're not a chemistry degree holding practicing chemist or anything, but you could figure out the density of polonium. And then knowing its unit cell structure is a little bit more complicated, but we can figure out its unit cell structure. Scientists have been able to figure that out long before things like atomic force microscopes and electron microscopy. And so from those two things, we were able to determine the atomic radius. We were able to measure a phenomenally tiny value. Okay, so let's do a similar example, but kind of working backward. How can we predict the density based on an atomic length? So gold has an atomic radius of 144 picometers. And based on the fact that I know we're going to want to have our density in cubic centimeters, let's just quickly convert this. 144 picometers is 1.44 times 10 to the negative 10th meters, right? And let's turn it into centimeters. That would be 1.44 times 10 to the negative 8th centimeters. Okay, so we have 1.44 times 10 to the negative 8th centimeters is the atomic radius of gold. And it has a face-centered cubic structure. And so the face-centered cubic structure says that L is equal to the square root of 8R. And that's all we need now to predict the density of gold. We know that the density is equal to the mass divided by the volume. Well, let's find the mass and the volume for a single unit cell. Okay, so gold is face-centered cubic. Do you remember how many atoms are within a face-centered cubic unit cell? We can flash this table up real quick for you. Face-centered cubic has 4 atoms, so we'll put 4 times, and then let's find our atomic weight for gold. Oh, you know what? You can't see what I'm seeing. I didn't realize that last time. When I was talking about polonium, you were probably wondering what is going on. But that's okay. So gold has an atomic weight of 196.97 grams per mole. 196.97 grams per mole. And we want to find the weight of a single gold atom. So that would be 1 mole is 6.022 times 10 to the 23rd individual gold atoms. So that is the mass of a gold unit cell. What is its volume? Well, that would be L cubed, the length cubed. And what is the length? Square root of 8 times R cubed. Okay, but we know R, so let's put that in. R is 1.44 times 10 to the negative 8th centimeters cubed. This one, we did that conversion up front, and so it's really just going to be a grand example of plug and chug math. So we have 4 times 196.97 divided by 6.022 E23 divided by, we're going to cube that edge length. The square root of 8 times 1.44 e negative 8. I believe I put that in properly, and I get 19.36, which matches the true value of 19.3 grams per mole. I guess it estimates it a bit high. We would technically want to round that up to 19.4 grams per mole. 19.4 grams per mole. Okay, again, pretty incredible that there's this link between the crude density measurement and the atomic length. Now, there's one last thing that we need to talk about here, and that is we've only been dealing with metallic crystalline solids. And so we're not going to do any math with this, but I do want to kind of point out that for ionic compounds, things are a little bit different because like every other position in the unit cell is like a cation versus an anion. So sodium chloride unit cell here looks like a simple cubic structure, sort of, in the sense that you have the ions stacked right on top of each other. But it also looks maybe like a face-centered cubic structure if you were to cut it the right way, because your chloride ions here are arranged in a face-centered cubic fashion. But unlike a face-centered cubic, the chloride ions aren't touching each other. And if we look at the sodium, they're also arranged in a face-centered cubic fashion. Again, they're not touching each other. And so, like, what do we call this? It's sort of like two different face-centered cubic structures that are intercalating into each other. And what we would really need to do is, first of all, what is this called? It's not any sort of structure we've talked about before. Ionic compounds have their own special names. This would be called a rock-salt structure. And what we would need to do is kind of look at this edge right here. So that's the length of a unit cell. And we can recognize that it kind of has one ionic bond length and another ionic bond length, right, separated right here. Chloride center to sodium center, and then sodium center to chloride sodium center. So one edge length is equal to two bond lengths, ionic bond lengths. And then, you know, instead of just having 4 atoms, you would have 4 sodiums and 4 chlorides. So you can see it gets to be a bit more complicated. Even worse is something like cesium chloride here. This definitely looks like a simple cubic for the chlorides. They're just arranged right on top of one another. But now you have the cesium that is occupying an interstitial space, and these chlorides are not actually touching each other at all. So this is more kind of like body-centered cubic, but again, it has its own name. So this is the cesium chloride unit cell, and you would have to go corner to corner, so this unit cell edge length would equal the square root of, it would, what is it, 4 over the square root of 3 times 1/2 of the bond length. Anyway, so it gets complicated. You don't actually have to deal with these mathematically, but I wanted to point them out. And it can get even worse than this. There is a unit cell called zinc, zinc blend with a fancy E on the end of blend. And if you look up zinc blend unit cell, you'll see that in just a Wikipedia image of it or something, and you can see that for the ionic compounds it can get really complicated. Just be aware that the mathematical treatments that we've done so far are applicable only to metals. They are the ones where all atoms are the same size, and we can really talk about an atomic length, radius instead of a bond length because of that, and it simplifies things considerably. So that's it. Sorry, this was a bit of a long section, but we did the math both directions, and it really all comes down to remembering that table 12.7. I'll put it up one final time. If you know these values, then you'll be good.